should be fine, but just in case it is not good, please do let me know. No, I will try to connect from other source. So please do let me know.
Sure, sir. Sure, sir.
Yeah, sure. So maybe I'll share my screen. Right. So hope my screen is visible.
Yes, sir. Yes, sir. It's visible.
Okay, great. So yeah, again, happy to take part in the second another session here in this nice workshop. Hope you all are enjoying this workshop. So in this next 1 hour, what I'll do is I'll try to give an overview of, you can put whatever names there you want, AI, ML, deep learning, data science. We'll try to give an overview of application of that in the context of medical imaging. I guess you might have already had few sessions giving an overview of medical imaging, and hopefully this session also will add some new points to what you have learned and make you think a little more deeper about that. So this is what we will do for the rest of, let's say, 50 minutes. Okay, just to get an idea of how the research trends are going in this area, one thing I did in January while I was teaching, that's the time when I was teaching this course, Deep Learning for Healthcare, started teaching this. So there you might all be aware of PubMed. So essentially indexes all publications related to medical imaging. So what was given here is machine learning word being there in either title or abstract. That's the first graph that you see there. And the second graph is publications that involve the keyword deep learning either in the title or abstract. So this is the graph that you see here. And yeah, now you can make interpretations about how you would like to see the trends there. Okay. So one thing I would say is if you consider anything above 5,000 publications, let's say, is where some serious buzz has started there. People have started working into it. You could see here that the term around 2018, the machine learning has entered into the field of to the medical imaging in a very serious way. Similarly, the deep learning, so-called deep learning, came around 2019-20. So within next few years, this has happened. And you could see this trend closely following the key developments that are actually taking place little upfront in computer vision. And yeah, we can make some more interpretations also from here. It's up to us on what level of interpretations we do. But for example, if you see the number of publications that came 20 to 21, if you see it almost doubled or added something like 5,000 more. And then also 5,000 more from 21 to 22. Now, then around 1,500 from 23 to 24, and only 1,500 around 23 to 24. So that means the honeymoon phase of machine learning, deep learning, where, if I may call so, right, where people were kind of publishing in a rush, or so many publications are coming, that phase is over now. Now, this whatever research area, if you plan to do as a faculty or as a student to do a research, you should be more picky on the topics that you choose and the quality of research that you do. Okay, that's the couple of messages that I would like to, or couple of inferences I would like to make from these graphs. Then AI, suppose these are, this is something I took from 2020 screenshot. AI in healthcare innovation landscapes, there are hundreds and hundreds of companies, if not thousands, which have spread across in healthcare, starting from analytics to mental health to nutrition, personalized healthcare, and particularly maybe in this one we are looking into imaging, diagnostic, and pathology. These are, you could see that there are really a booming phase in general, or a very encouraging phase in general for AI in healthcare. That's how you could see it. Now, by this time, some of us would be using the word AI some of artificial intelligence. Sometimes we call this as machine learning, sometimes deep learning, sometimes data science. Okay. So what do they really mean? How are they different is something perhaps you might have already started contemplating about. And this is put in a slightly lighter note on when you call something as statistics, something as machine learning, and something as AI. But again, having told on a lighter note, but this is not too much of an exaggeration. It is not too far from the truth as well. So when you are implementing, it might be logistic regression, softmax regression, linear regression. But when you are hiring somebody who wants a regression, regression is you can think of it as a classical statistics problem. But when we look for students and all, we say we are looking for somebody who works in machine learning. And then you want to raise funds, you want to say to a layman about it, then that's where you use AI. So if you refer to any two books, no two book, if you refer to any number of books, no two books exactly have the same definition of when do we call something as machine learning, when do we call something as deep learning and AI. Of course, on a broader scale, you could say something which is generic umbrella is AI. And under that, you're using a lot of data to learn. That's when you call it as machine learning. And when this network architecture is too deep with too many layers in between, that's when you call it as a deep learning, you can say. And then you will see that's how I would say you could view at this terms before. I'm just trying to bring some clarity or rather confusion about these commonly used words in because this is something we are going to get trying to get an overview here. Okay. And then the genesis or the roots for all this machine learning, deep learning algorithms that we see today have come from computer vision. So want to draw your attention to the point that the kind of problems that we address here in machine learning, in medical imaging are not too different from what you see in computer vision. There are set of problems that are almost similar to what you see in case of computer vision. For example, in computer vision, you call it as an object detection. Here you might be looking at a disease detection or an abnormality detection. Or these days, methods like segment anything, you might be trying to detect one organs and other things. On one side, you do their object classification. Here, within the disease, there could be different classes. So disease or injury classifications you might be doing. And then there you do segmentation of the objects. Here you do segmentation of the organs or tumors. Then you might be tracking an object there. Here, maybe let's say for a robotic guided surgery or for the doctor to assist with these all these developments in medical imaging algorithms, you might have organ tracking superposed over the patient and all. So these are some similarities. Nevertheless, we do have problems that you can say are unique to medical imaging. For example, there are we have data for a big population, and in that we want to find out if there are some patterns that you find out for a particular group of a particular group of people that comes under detection of patterns and all. And then it's not just structural imaging that we have here. Hopefully you got a chance in one of these sessions, or hopefully you will get a chance to look at the functional aspects of imaging like fMRI. In those cases, analysis of functional images is slightly different from the conventional computer vision problem. And another thing you could see these days, one of the key research areas that's going on is multimodal imaging that they refer to, where this multimodal doesn't mean different modalities of imaging, but it is like non-imaging data. That's what, for example, there is a textual information. For example, there are some prescriptions written by the doctor with some symptoms. This is a non-imaging textual data is there. Or you have gene information coming for that one. Genetic information is there. How do you incorporate this genetic information also into your deep learning algorithm? So this is again one of the hot areas. So what I am trying to kind of convey here is that while there are quite a few similarities between computer vision and medical imaging, nevertheless, there are problems that are unique to medical imaging. So another thing that I want to draw your attention to is that the challenges that we come across in medical imaging, we do have some unique challenges, not only unique applications that we saw in the previous slide, but also there are some challenges to be addressed, which are not so, perhaps not so severe in many of the computer vision applications. For example, the first one you could say is you have already seen your CT images, MR images, PET scan images, or other modalities. They are 3D in data, and some of them are 4D in fact, where the time is also there. Over time you acquire these images, you want to analyze these images, which means the number of voxels or number of, you call in a two-dimensional, we call this as a pixel. The volumetric element is referred to as voxels. So these are very large here. The data size is very large. That's one thing. Second important thing is the images for training that you get in medical imaging are far, far less than what you get in case of medical imaging. Because this is when someone from computer vision background says that I have a reasonably good size of data set, remember that he is talking of the order of 1 million, which can hardly be obtained in case of medical images, because typically the images that we have is 100 to 1000 images. Here we are talking about training images. When I say training images, what we mean here is the annotations are also available. For example, which kind of injury it is, or for that injury doing already the segmentations part. So the number of, now we need to live with, we need to develop effective algorithms that can learn the required features and do an efficient job for us with limited data set. Not only that, but there are some abnormalities that we come across, which are some rare diseases. So there are within the images, for example, if we are doing classification, there are some images for which we have very small sample size. So this is another important problem that we come across in particularly in medical imaging. Another thing is getting data is very expensive, training data, unlike in medical imaging. This is also okay, we can attribute to reason being why we don't have such a large data sets of repositories of images. There are few exceptions. For example, the chest X-ray data set, which has around 1 lakh images. And then for head scans and all, RSNA data set. And then for brain tumors, there is another the BRATS data set. There are few exceptions to it, but overall, largely getting annotated training data is expensive, because it is the doctor who has with the clinical expertise is the one who has to sit and give us all this annotations. If it is a computer vision problem like detection of objects, it can be done by anyone, including us. But medical imaging does require expertise. And not only that, training data is sometimes imperfect. For example, we want to say a disease, for example, it's a so-and-so kind of tumor is there. But not in all cases, this could be correct. For example, unless one does biopsy, we assume that we cannot confirm whether it is belonging to a so-and-so class of abnormality, but not in all cases biopsy can be done. So there are various practical factors that kind of limit the data we get. So it's important that if you are going to start your research, these could be some guidelines you keep in mind, so that you can pick a problem which is unique to, or which is specific to which is very prominent in medical imaging, which is very important to be solved for medical imaging, and try to find solutions for that. Okay, so the purpose of the rest of the talk for me is twofold. First, I would tell you some of the mention about some of the success stories which we will see now right away. And after that, I want to also put a cautionary post. At least maybe in the interest of time, we can touch upon few topics only, some cautionary things. The floor is slippery, like in many other areas. Medical imaging also has a slippery floor. So where we have to be cautious. It is by no means pessimistic. It's rightly said as cautious thing. So we need to figure out, it's not just looking at finally how much accuracies I got and all, but you need to pay attention to some aspects. Will anyway, instead of making a generic statement, I will illustrate that with some examples. Okay. So as I said, there are quite a few success stories in medical imaging. Here are some images that you could see here. The first one is mammographic mass classifications that you could do from mammographic images that we have seen in the class on the previous session. We have seen that. So this has reached accuracies which are on par, if not more, than a clinical expert. From deep learning these days, you can get. The second image in the first row shows you the brain lesions. Again, there is a one conference that keeps, one challenge that keeps on running on this, and it is able to, now you are able to get very good accuracies from that. And the third one you see is about airway leakages that can be computed again from the chest CT scans, and it has achieved very good accuracies in finding out the air pathways and the leakages. And the second row, first one is about diabetic retinopathy, where there is some clotting or whatever is happening, abnormalities happening there, or blood vessels, change in blood vessels shape and all can be detected. And, and diabetic retinopathy application also, now there are tools that clinicians started using. Similarly, about prostate segmentation, and this is, I think, uh, this may be the breast cancer metastasis, and skin lesion classification. Again, you will see a lot of data sets now available for that. And this is for the bone suppression from CT images. Again, this is not so prominent in India. Very few scanners we have, which are dual energy CT scanners. So using to acquiring two images with different energies, we could mathematically also model that to avoid bones, to suppress the bones, so that the rest of the analysis can be done on these images, so that if we are interested in lungs, they are more visible, then the result is somewhat getting hijacked with the structure of the bones or the variations that we observe. So these are applications that have been well established. As I said, want to put a cautionary post here on application of machine learning to medical imaging. That's one of the objectives of this talk. As you would be anyway have been listening to a lot of hype, which is true to a great extent perhaps, but again, it's important to be cautious here. So this is something I took inspiration from Professor Jayant Haritsa sir from IISc Bangalore. So he mentions that this is what the right now the people talk about the data science. Okay, similar thing is applicable for machine learning, deep learning as well. The kind of statements that people keep making is data is the new oil, data science is the new quantum mechanics, and there is some acronym commonly used to say anybody can dance. They say it ABCD. Nowadays, there are so many training centers coming all around who will tell you that you can master data science in just 3 months. You join our course and you will become. So just like anybody can dance, they say it's almost like saying anybody can do data science. Okay, this is a nice witty acronym tossed with that expansion being tasked by Professor Jayant Haritsa in one of the lectures I was attending to. Right. So the reality is that, so very few of us have an idea on why in the first place this is called as data science. Okay. So suppose I have data, where is the science in it? If there was time, ideally, I would have asked this question to you all and would like to hear some responses. But in the interest of time, I myself put the question and I'll myself answer that. So where is science in data? Why do we call this as data science? Very few of us keep thinking about this. But why this is called as data science is it essentially tells us the scientific way of analyzing data. That's what it means. So that means here the emphasis is on the development of this understanding, developing and implementing scientific methods is very, very important. So that science part, if you want to put it that way, not exactly the science here, we mean the scientific approaches. Understanding of the physical, mathematical principles is very important. Then there is again a quote by a Nobel laureate, which tells you that if you torture the data long enough, it will confess to anything. So if you use a very big network and you give a training, it has millions, hundreds of millions of parameters, and it may appear it is giving you the desired output, but there should be some sanity checks that one should do before arriving at any conclusions. So to illustrate that, maybe I'll take 4 to 5 examples to you on why we should be cautious and where we should be cautious, perhaps some of the areas I would show you. Okay, suppose I tell you like this. Maybe I wish you had, I hope, I'm not very sure you had any another session on explaining about within MR, there are different kinds of modalities are there, T1 weighted, T2 weighted, flare imaging. There are so many varieties of that, diffusion weighted imaging and all those things are there. Suppose if I tell you, so you are all aware of GANs by this time, which is generative adversarial networks, which essentially generate synthetic data which looks are very similar to a realistic image. Say, for example, I take pictures of pizzas, okay, and I also have T1 weighted images. What I could do is I could train a network for which if I give a T1 weighted image, it can generate a shape, an image of a pizza. On the other hand, I could also give a pizza to that GAN network. Hope you had some session on GANs. Otherwise, as I said, this is something which synthesizes the realistic looking images. So assume that I have 100 pizza images. I have 100, I have taken 100 T1 weighted images. I'll pair them myself. Now I'll say that if I give this pizza image, you should give me the T1 weighted, this T1 weighted image. If I train it so on and so forth, next time at the time of testing, if I give a new T1 weighted image, it essentially learns the distributions of both and then converts one from one to other and will give me the next one. Okay. Maybe you might be thinking I'm going crazy here. Why would anyone would consider generating from pizza to T1 weighted image? I'll make this more realistic. What I would say is the story I will slightly change the narration now. Now, there is, you already know MR. In MR, if you know diffusion weighted image, very good. Otherwise, consider that as just one version of MR image. Getting MR image acquisition is expensive, time consuming. You need to have that scanner in the first place to do that and all. So now the idea is this. Suppose I can build a deep learning network for which if I give CT image as an input, if it can synthesize for the same patient an MR image, is it not great? I could then don't have to go through MRI scanning. I can simply take CT scan, and from that, for the same patient, the equivalent MR image can be generated. So here you could see here, this is what the MR image it synthesized, and this was the actual diffusion weighted image that acquired for the same patient. And anatomically, more or less, it looks same, but you could see here this bright region which you see in this last image is in fact a tumor there, which this GAN network cannot do. Why I am telling it is, while it would have looked funny to you, generating from a pizza to a CT image, you will see hundreds and hundreds of papers, if not thousands, where GAN networks are used to synthesize MR images from CT images. But again, see suppose when there is some physics underlying while we acquire these images, just like something which you can see using visible light is different from what you see from an X-ray. When the signal has changed, what you could see also changes. In the same way, if your data is having a bias towards normal subjects in your data, more majority of them are having these kinds of things, then you can never expect it to robustly and what you could say is faithfully find this out the tumors there. So this is again coming from a paper got published 2019 paper, a review of GAN networks used here. So that's one thing I would like to draw your attention is while you are synthesizing images, the synthesis that we do here is not, you should not look at it in the same way as we do in computer vision. So underlying principles, if the data that you are looking at in another modality, if it is inherently there in the modality that you are giving as an input, you could expect to generate one from the other. But if the input modality doesn't have this information either latently or inherently, you cannot, this is not something that deep learning can do. So it is something that should complement our intuition and the physics principles that we know, but it should not be seen as something falling from the heavens that could do magics for us. Suppose if you are in your data, you don't have many of these tumors, from the evaluations, it may so appear that you are able to faithfully generate these diffusion weighted MR images from CT, but the very purpose of going through these scans is to recognize these abnormalities or these rare things. So that is where one has to be very cautious. So this is about the first point I wanted to make is about synthesizing the images. So the second thing I wanted to draw your attention to is the correlation versus causation. So to explain this, let me take an example. For example, we have all seen the COVID time. During the COVID time, all of us, most of us are staying for the most of the time at homes. Since we are staying at homes, there are no thefts there because there is no time window for them to come and do the thefts for the thieves. Okay, so there is a drastic decrease in number of thefts that happen. Now, there is also no social life because of this COVID. People are restricted to stay between the four walls or within the four walls. And because of, and those who got used to a lot of activity otherwise till then are depressed. So lot of depression cases have also exponentially increased over COVID time. Now, consider a machine learning algorithm. It is trying to predict something to which I give over a period of time how many thefts had happened. That is one as an input. And another parameter output or another parameter I'm looking at is how many cases of depression are there over every year. If you look at it, you would see that you can in a hasty manner, if you implement this without paying attention to the nuances, you'll find out that with the decrease, with the decrease of thefts, depression cases have increased. Is it not? You would see that same trend in both these things. But we have to, there is some correlation between the thefts, decreased thefts and depressions, but one is not the cause of other. The cause for both of them is COVID. COVID has decreased the thefts. COVID has increased the depressions, but not the case of thefts, decreased thefts increasing the depression. So again, you will see lots of works published. This example might look so trivial, so obvious to you, to all of us. But if you see it, there will be huge amount of literature in medical imaging where they say, but for so and so abnormality, that particular part of brain is the cause. If there is a in volumetric change in that, this will happen. But a very careful study of, is it a causation or correlation? Just a correlation has to be understood here. So this is one of the slippery areas where there should be a cautionary post. And one you should look at, just like, okay, I can predict from my network this thing very accurately if you say it. First of all, intuition should follow deep learning, but not the other way around. So this is again something I want to bring your attention to. And another third very important thing in medical imaging in particular, more than any other area, I would say, is explainability is extremely, extremely important. If we just say that, for example, a particular patient has so and so abnormality, or saying that this is the ideal treatment for him to follow, that's not good enough for the doctor to buy this statement. So all this, whichever a machine learning or a deep learning algorithm in for healthcare suggests or recommends, should come with a rational. Again, nowadays, if you plan to do research in this area, explainability is a very, very important area as of now, and there are a lot of things to do. So what do we mean by explainability? I would just quickly mention about it in one slide here. For example, yeah, sorry to stick to still the COVID examples, although this is past. Okay, so that's where explainability, because we are all went through that, we can easily correlate with those examples. One way of giving it telling is the algorithm telling whether COVID positive or COVID negative. But again, that is not good enough. How does the doctor can have confidence on what it tells? Instead of that, then another way of telling is, look, I come this algorithm as an algorithm, I came to the conclusion because some abnormalities are observed in the areas that are highlighted in this image. If the algorithm gives you the regions which have predominantly influenced it for arriving at that decision, that's one kind of explainability on why the algorithm tells that this has an abnormality. This come to the conclusion, but that this is positive or this is negative. Another kind of explainability is the algorithm retrieving images which are very annotated earlier and are there in its training repository that look very similar to current image, and that led it to arrive at this conclusion. So now the algorithm tells that I say I came to the conclusion that this image corresponds to a person with COVID because the patterns that I observe in this image are very similar to these 5 images in my training data, which you have annotated as COVID positive in those areas. So this is another explainability. So this is again another very promising area. And this is something now if you plan to publish in good places, some element of explainability about these algorithms, at least to the level of class activation maps and all should be there to ensure that the inferences are made by these algorithms by looking at the right areas. Okay, so that's the third one I wanted to highlight to you. So the just to summarize, the first one being synthesizing one image from the other, second one paying attention to correlation versus causation, the third one about explainability. The fourth one I want to draw your attention to is called as out of distribution. Okay, consider now that your algorithm, for some strange reasons, you want to count the number of bananas, or if there are bananas, you want to detect that. Being from India, good to see the pictures of bananas, so many varieties, right? Suppose your algorithm has been trained on the data on the images similar to the one which you see on the left hand side, and now all of a sudden during the testing time, if it come across as a different kinds of bananas that you see here, what is that you desire the algorithm to do? One is it makes some inference, draws some conclusions based on that, or the is it not the other sensible thing is to say that the image that I have been given now for predicting is outside the distribution of images that I have been trained on. Hence, I won't be able to make an inference or make a prediction on that one. So, it is in another word, learning the distributions and then saying that when in an image at the time of testing is outside this distribution, it is just saying that, no, this is not my job. I am not trained for it. So this is out of my distribution. So this is again another very, very important area. If it come across some abnormality, doctor doesn't want that it will be put into one of the baskets of possible diseases or abnormalities and the algorithm to keep quiet. Rather, more sensible one is, I'm not trained for it. You are the one to take a call. I have no idea about how to do this. So this is called as out of distribution. Again, a very promising area. So I'll just, maybe in the interest of time, I'll take one more area or topic I would say is somewhat similar, but not exactly to what we have seen there, is called as uncertainty estimation. What it means is, you don't just give what is, for example, you want to, this is the work in presented in ICV-GIP this year. So where the job is to say whether there is a bleeding in a given image or frame or not. So in addition to saying whether there is a bleeding or not, if the algorithm also tells that with this much of certainty, I can tell whether there is a bleeding or not. So this is like attaching how confident you are about the attaching this confidence value to what you are going to infer. Okay, so then the way you could see is, for example, it's okay to have some false negatives. Hope you are all by this time are clear with what it means by true positive, true negative, false positive, and false negative. And we say false positive means something is actually positive, then, or something has been told as positive, but it has been told falsely as positive. That's what called as false positive. Another thing is false negative. That means something is not negative, but has been falsely told as negative. Usually, positive, negative, we use in the meaning of negative, positive. To say on a lighter note, COVID positive means he had COVID. Similarly, here when we say positive means he has that abnormality. Say, for example, when your algorithm says no, it doesn't have any abnormality, you want to see with how much confidence, how much certainty you are able to say. And if the certainty is well below a particular value, then you will not take a call on yourself, similar to what we have seen in the previous topic, previous theme. Here, then the decision like in out of distribution, but this is slightly different problem here. The uncertainty comes for various reasons here, not just out of distribution. It could be other things as well. So here, then you will leave the decision to doctors. So this would false negatives by this manner would be drastically reduced, and the system becomes more reliable here. So to summarize, so integration of domain knowledge with ML models is the way you have to look at it. That is very, very important. So as I said, first the intuition ML models should give you what the intuition or the domain knowledge says, clinical knowledge says, but not the other way around. And again, the second one we discussed is about causation versus correlation, explainability, uncertainty. And again, if you plan to work in this area, other very important topics to look at are development of generic models that work across different scanners. We haven't touched it upon in the interest of time. And then distributed learning or federated learning. These are all very important topics because data from different sites, sharing that will be a problem. On the other hand, they may allow you to kind of train your model on their data. This is another important one. And finally, if these models need to be deployed at the site, they have to be lightweight. So this is another important topic. Okay. So again, it's not out of context to quote this. Andrew Ng, I think this was from 2000. I'm sure you all know Andrew Ng by this time. You would have heard. So he was putting a Twitter statement that should radiologists be worried about their jobs because these healthcare things are doing very well? And 2017, around the same time, Jeff Hinton, the godfather of he is called as the godfather of AI. You all know he got the Nobel Prize also this time. He who was saying you should stop training radiologists now. But the truth is slightly, or significantly rather, is different. Again, the RSNA is an important body which looks into radiology in AI. So they are making statement modifications to that, saying that the question to pose is not will AI replace radiologists? We would say no, but the right perspective is radiologists who do AI will replace radiologists who do not. So we can kind of extend this and see that will domain knowledge be replaced by AI? Definitely not. But perhaps domain experts who do AI also may replace those who are just means again. That's one way to look at it. That AI definitely has its own place, but not at the cost of domain knowledge. At the same time, a nice amalgam or integration of both is the need of the hour. So maybe I'll stop here since there are 10 minutes. Yeah, I thought of giving you some flavor of what kind of work we are doing in this area also, but maybe it's good to have some time for questions and answers. So maybe I'll take a pause here.
Yeah, thank you so much, sir, for your wonderful presentation on the challenges of AI in medical imaging, and mostly the importance of, uncertainty, and there are several others like out of distributions.
Right, right.
How this generative AI is going to be useful, whether it is really important for us or not. So these are like important aspects of medical imaging, as we all know. So participants, I request if you have any queries, so I will happy to take questions.
Hope they can, yeah. If you have any queries, you can type there. I'll try to read it and answer that.
I think such that they can write their queries in the chat box. We need to check the chat box.
Yeah, I opened this chat and looking for any of the queries there. Sir, will AI replace doctors? No, definitely not. That's exactly what our RSNA also says. But doctors who do not use AI could get replaced with doctors who use AI. So I think that's a very sensible statement. Just like these days, you look into any conference and journals, and sometimes those who work on the classical things on a lighter note, it looks very depressing to see those journal papers and conferences because you hardly see any work there which do not use AI ML these days, right? So in the same sense, but again, can we come to the conclusion that there is no point in learning the domain knowledge? Definitely not, because it is the domain knowledge that guides us to come up with the right models, simple models, without actually having a very heavyweight models. So that's what I would say. Could there be an implications of uncertainty estimation when used in addition to XAI methods? Yeah, means these you could see as two independent things. Explainability and uncertainty is telling you with what accuracy you could say, but what led you to that lowering of accuracy is not given by that uncertainty estimation. So that way I would say each complement the other, and not like one versus the other. That's how I would see. And the next one is behavioral data and MRI data combination can be used as a multimodality. Yes, definitely, yes. Nowadays, even usually the wave begins in computer vision, then that will be adapted by medical imaging, and there are many other such domains. Even there are other domains which adopt those things later. We could see mechanical engineering, some areas when I interact with colleagues and all, something which were done 5-6 years earlier. Now they go a little slower. So it's like the wave goes. There are all these spatially located you could think of. And now you could see the wave in ICCV, CVPR, and all this computer vision conferences that the multimodality has suddenly, that wave has come there. So now that's the kind of thing, if you want to get hold of some new topic where you could make contributions, multimodality is definitely the area. And as you said, suppose doctors, they typically have one checklist kind of thing, behavioral patterns might be there. So how do you include that non-imaging data into imaging is very good area. So that comes under behavioral data and combination. You could think of it as multimodal. Okay, thanks for the information. And Gyan synthetic data, I expected difficulty to collect CTF. Yeah, don't do that. That's what I am telling you, because as we were discussing, there are some patterns. The very, but again, while making this statement, let me also, as I was mentioning, there are hundreds and hundreds of publications which got published that time, fortunately or unfortunately, where they say that you don't have to go through MR. We have collected enough number of pairs of CT and MR. Now you just do CT, but you get MR out of it. But as I said, intuition, the deep learning method should follow the intuition, okay, but not the otherwise. The horse should follow the one driver, but not driver should not follow the horse, okay, the horse being here machine learning, not the other way around. Because it has no idea on what it is giving. So I would say don't attempt that. Good that you find it difficult to acquire the pairs of data and you did not do it. On a lighter note, I'm saying. Okay, out of higher sensitivity and specificity, which one is better to go? Very good question. Should I go for high sensitivity or high specificity? Depends on what you are doing it. Suppose if you are doing a screening test, let's say. Screening test, I'm sure you all know. Screening test is not a final diagnostic test. That's where even a iota of doubt, if you have it, you want to consider it as a positive, and then you want to do further tests to rule out whether it is positive or negative. So in such cases, if you have false positives also, it's okay. So then your sensitivity is high, your specificity is low. Ideally, what you would say is, I want sensitivity of 1 and specificity of 1. Then that is not possible. If you hope you are all know the definitions of what sensitivity, and I am assuming how sensitive, to say it in layman's terms, how sensitive is the proposed method to a particular one. When we say that, that means if it is there, can it detect or not? That's only. If it is not there, it is not worrying whether it is detected as positive or negative. Specificity is exactly the other way around. So it depends on the context. If you are doing a screening test, that means it is like now we do screening for IIT JEE exam. That means that the first one is the screening, second one advanced, let's say. Yeah, that means even if we want those who are meritorious want to get through it, even some who are not meritorious being through that exam is also okay. But those who are meritorious should always, we want to ensure, go through it. In the same way here, when we say somebody not having, for example, pneumonia, you still, if some of them under the screening test are potential for pneumonia, if they found it, you are okay, because you are going to follow it up with something else. So it depends on the context. Ideally is, of course, having to high. Then other question is, out of higher sensitivity and specificity, and how can the out of distribution be determined? Can the current machine learning? Yes, there are ways now. There are, of course, if you are aware by this time, if you are doing a MICAI medical imaging workshop, I'm sure you are all aware of MICAI conference. If not, you should be aware of that. Go and Google what it is: medical image computing and computer assisted intervention. So every year it happens, annual conference. Along with that, it hosts a lot of challenges. And I think the challenge name is Shift, SHIFT, Shift. It has its own this expansion, which I don't remember right away. There are a lot of there are at least 3-4 applications that they considered on how you detect. This is a very, very interesting problem where you learn not only the weights and other things, but to figure out whether the input that you are getting next at the time of testing is falling under out of distribution. It has its own sound mathematical background to it. Please do go through them. As I said, along most of these challenges are posted on grandchallenges.org. So you just, when you Google this, grand challenges in medical imaging, more often than not, this would be the link that you would get there. So please, if you want to work in that area, see the challenges so that you have annotated data, some baseline methods already available, and you can build on top of them. So that's the last question that I could see here. Yeah, we have a few more minutes. If you have any queries, you can post, or if I had missed, hopefully not, any of your comments, please do repost here. Yeah, if there are no comments, so then maybe it's good to have for you some at least a small break before your next session starts, I guess at 6 o'clock.
Yeah, thank you so much, sir. Once again,
My pleasure.
on behalf of the and ICT Academy, the Department of Computer Science and Engineering, we are very much thankful to you for joining with us, and we look forward for possible future collaborations with you.
Sure, my pleasure, and thanks for inviting me. It's very nice interacting with all the community who are working in the area of medical imaging. Wish it could be in person, but this is the best thing that can be done at this point of time.
Maybe in future, sir. Maybe in this future.
Yeah, right. Thank you all. All the best. Yeah, hope I can sign out.
Yes, sir.
Thank you.